of smoke, and I think it may trigger fire alarm in the lab. But regarding the second problem, so the question, you may probably correctly answer that the element we were talking about is chromium. And the experiments the teacher did were as follows. So this is a compound which the teacher took originally. It's sodium bichromate. So it's orange solid, pretty soluble in water. And it produces a nice orange color. Let's make it more dilute. Again, the experiments go much better when I see your faces. So again, if newcomers enable video, that would be much better. So then, if you add the base like sodium hydroxide to this solution, the solution changes the color. Now it's yellow. And this process, by the way, this process is reversible. So if I add acid back, the color changes to orange. And I can continue that again and again, and the color will continue to switch. Although the solution, it will be more and more dilute, but it will be, it will change from yellow to orange. Now, if we add I changed the conditions of the experiment a little bit, but it doesn't change the meaning. So if I take this and add the compounds called the sodium sulfide, the color changes to, I don't know if you can't see it, but maybe it's better to dilute it. So I just dilute it in water. Add more. So it is yellow-green, right? And finally, if I do, instead of, to accelerate the reaction, instead of taking metal foil, I take, what? You wanted to ask something? No? Okay. Instead of adding metal foil, I add the powdered metal, the zinc powder. So I add more acid, and zinc, finely divided zinc. 6 to 9 micron. Very, very finely divided metal. It has a large surface, so the reaction is fast. So let's see. So the reaction, we need some time for reaction to proceed. And there are bubbles. Bubbles are forming. Okay, let me add more acid to accelerate the reaction. Okay, let's dilute it to make color more visible. So the color is blue, right? Does everybody see the color, or I make it more? Okay, let me make it more dilute. It's not transparent because the zinc dust still makes a solution turbid, but does everybody see the blue color? Use these two. So in total, we have yellow, green, blue, orange, and yellow. Oh, that's a different color. So different chemical. And yellow. So the whole spectrum of color, that's original color, that's the color after addition of sodium hydroxide, that's after addition of sulfate, and this is after addition of zinc. And all these color transformations are due to the change of the valence state of just one metal, chromium. And chroma in Greek means pigment, dye, and the name of chromium, the name chromium was given to this element is specifically for that reason, because different valence state of this element produce different colors. And what happened? What happened during these transformations? By the way, let me do one more demonstration. I just realized I can do something else. Okay. So what do we have here? So sodium dichromate, the compound that we that is the orange, as an orange shape, is this one. The formula looks a little bit scary, but in reality, it's the analog, the close analog of sodium sulfate. Because what is sodium sulfate? Sodium sulfate structural formula is this. And if we draw the structural formula of this molecule, it will be pretty much the same. Actually, the formula of sodium chromate, the yellow one, looks exactly the same as the formula of sodium sulfide, which is the classical, typical salt. This one, the yellow solution. This. But what happens when we add an acid? The acid, in the presence of the acid, this sodium actually it exists in the form of the ion, right? Because it dissociates in solution. So it exists in the form of an ion, double charged negative ion. And sodium just travels freely in solution. But if we add an acid, the hydrogen comes here. And that makes, and if two copies of this molecule come together, they make kind of a dimer with the elimination of one molecule of water. So this oxygen of the second copy of the molecule attack chromium, and this OH leaves. So we have two copies connected together via the oxygen bridge. But if you take a look at this, okay, let me finish drawing. So this ion is yellow, this ion is orange. So this is a transition. This transition occurs in the presence of acid, and in the presence of base, the opposite transition occurs. So why it is reversible? If you take a look, who can tell me what's the valence of chromium atom? What's the oxidation state of chromium atom here? Who can tell me? And how can we calculate the valence state? Just a number of bonds. Here you draw a circle. And how many bonds does this circle cross? Who can tell me? Who can count? Who was good in math in elementary school? How many bonds this circle crosses? Hmm? Can you speak? Oh, I know what's the problem. You disabled your microphones. Can you please unmute yourself and answer? How many bonds, how many lines this circle crosses?
6.
Exactly. And how many lines, if you draw a similar circle here, how many lines it crosses?
Also 6.
Yes. And here. And here. Also 6. And taking into account that oxygen always pulls electronic density from chromium, and both from chromium and sulfur, this is +6. The oxidation state is +6 because the electronic density is withdrawn from the element, from this atom. So, in other words, this transition and that transition does not lead to a change of the valence state. The valence remains the same. Chromium remains 6 valent, and the oxidation state is +6. And that is why it is reversible, easily reversible in the presence of acid. It comes from yellow, it transforms from yellow to orange. In presence of bases, it's transformed to orange, from orange to yellow. But what happens when we add the sulfide, SO3, SO3 ion, sodium sulfide? What's the valence of sulfur here? Who can tell me? How many bonds are crossed by this circle?
4.
Yes, and that means sulfur can be oxidized further because its lovely oxidation state is 6. So it can take one oxygen, can make 2 extra bonds. That means it is a reducer. It can reduce some species that can donate oxygen that are in too high valence state. And that's what happens when you mix chromium, 6 valent chromium, CrO, I don't know, Cr2 or 7, 2 plus this ion. When it is mixed with sodium sulfate, sodium sulfate takes away all the oxygens, and chromium becomes trivalent, triple charged, positive triple charged chromium. And this is yellow-green or green. Oh, yes, green. This solution, yellowish greenish. It's not clear, not pure, but that's a kind of reaction is not complete, but yellow-green. That's a trivalent chromium. But if we take some chemical which is kind of donates electrons that can be oxidized much more easily, and donates electrons easily, it can provide chromium with one more electron. So the chromium becomes divalent, Cr2 plus. And this divalent chromium is blue. Oh, by the way, this is blue, but this is very unstable, so it may react even with atmospheric oxygen and start to oxidize. Sorry, like this, and oxidize partially back to Cr3 plus. And while it was standing, you can see it is transforming from blue to green blue, because it is evidently taking oxygen from the atmosphere and oxidizes back to the +3 state. So in summary, chromium alone can provide almost all colors, can yield almost all colors in a rainbow. So it's very, very nice, colorful element, hence the name. But what is the reason? What makes chromium so specific? Actually, it's not really specific. Many other metals form many different valence states, although colors are not always that bright. and color change is not that evident. However, why? Which metals are prone to that? The metals that can exist in many valence states are called transition metals. And they have one very specific feature. But first of all, what makes metal a metal? Which structural features make metal a metal? This feature is the presence of loosely bound electrons or electrons on the outer shell. If you take a typical metal, typical active metal like sodium, it has the dense core. For sodium, this is a kind of neon atom plus one extra positive charge. And then the outer electron, which occupies very big orbit, it's far from the core, and it can be easily donated. And when the sodium cannot donate, the sodium atom cannot donate it to anything, it donates it to the bulk of metal, to the piece of metal. Because even when sodium is a piece of metal, sodium, the atom's own electrons still do not belong to them. They are shared, they are freely flowing in the bulk of metal as the electron gas. And this is a property of this electron gas that make metal a metal. Due to this electron gas, the metals are conductive, because electrically conductive, because when electrons are flow, the current, electrical current, is actually the current of electrons and the current of this electron gas. For the same reason, the metals are thermally conductive, because the vibration of atoms in one part of metal are easily transferred to another part of metal, because electrons transfer this momentum. They are malleable, they are non-transparent. Non-transparency is also property of electron gas, because electron gas quenches efficiently any electromagnetic radiation. And they are lustrous, they have a metallic luster, again, because the electron gas interacts with the incident light on the surface of metals. And reflects all light in a different manner than any other lustrous bodies reflected, but that's a separate story. But what is the core? What is the core phenomenon that? And if you ask any physicist about metals, the definition of metal will be exactly the same. The body, which is malleable, non-transparent, lustrous, with metallic luster, electrically conductive, and thermally conductive. These 5 traits allow us to claim some element some substance is a metal. But what all these 5 features come from? From loosely kept, loosely bound outer electrons. So all those features are connected to just one phenomenon: the presence of outer electrons, which are loosely bound to the atom. But in typical cases, the core, as soon as a metal atom lost their outer electrons, usually 1 or 2, the core is stable, and it is not perturbable by chemical means. However, that is the case for true metals like sodium or barium or I don't know, calcium, because when calcium loses two outer electrons, the core is the argon atom, which is non-perturbable, extremely stable. But for transition metals, the core contains the d orbitals, which are usually partially full and which are perturbable, which may continue to donate electrons. And for example, for chromium, the d orbital contains extra 4 electrons in addition to 2 outer electrons, and they all also can be donated. But when all these 6 electrons are donated, this element, this atom does not resemble metal anymore, because again, the metallic feature, the main metallic feature is the electrons at the outer orbit. But if there are no electrons at the outer orbit, it's not a metal anymore. It starts to behave like sulfur, like non-metals. And that is why sodium chromate behaves like sodium sulfate. It looks like a salt. It is dissolved, and the chromium plays the role of a non-metal sulfur in this compound. In other words, transition metals are elements with the kind of dual nature. When they are low valent or they are free elements, they behave like metals. But when their valence is high, it starts to behave like non-metals. Chromium is the analog of sulfur, vanadium is the analog of nitrogen, manganese is the analog of chlorine, and that makes transition metals so interesting. In addition, transition metals can donate all their electrons on the outer shell and d orbitals, or just part of them. When chromium donates just 2 electrons from the outer shell, it is a divalent, it is blue. It can donate 1 extra electron from a d orbital, and it becomes trivalent. But it can donate 3 more electrons to become 6 valent. And all this diversity is the specific feature of transition metals. And that is why their chemistry is so complicated and interesting. Okay, now, now we can switch to the topic of this month, the energy, the heat of reaction, and so on. Although I didn't do a demonstration for the 5-point problem, you can easily find this video on the internet. You mix permanganate, potassium permanganate with glycerol, and if in several minutes the violent reaction starts, very, very violent reaction, which usually leads to causes fire. Just Google, type in YouTube potassium permanganate and glycerol, and you will see this video. And again, the story is the same. Permanganate is similar to, okay, if you take a look at this, you will, permanganate is like, manganese is the the element is atomic number, is a neighbor of chromium. So its maximal valence is 7. So permanganate has a formula of this, like this, and it loves to be reduced. It loves to accept electrons from other chemicals, and it may react with any oxidizable compounds, and glycerol is a oxidizable liquid is a very, very good candidate. And when you see a violent reaction which leads to evolution of heat, that's obvious, that's reasonable to conclude that the starting compound has a higher energy and a low stability, and it transforms to more stable compounds, and excess of heat, excess of energy evolves in the form of heat. So that's a totally straightforward and obvious. Indeed, if we take a look at the simplest possible reaction of that kind, hydrogen burns in fluorine. It's a very, very exothermic reaction. And it forms two molecules of hydrogen fluoride. I draw structural formulas to make plus a lot of heat. Q, it's usually we denote the heat denote with the letter Q. The question is where this energy came from. What changed in this reaction? The change is these bonds, right? These two bonds broke, these two bonds formed. That means this energy is the energy difference between these bonds and these bonds. So this bond is more stable than this. And that is why this bond has higher energy, this bond has lower energy. This bond has a higher energy, and this bond is lower energy. And it is quite obvious that that is why this reaction occurs, but the opposite reaction doesn't. However, if we conclude that the energy, the heat, is the kind of excess of energy produced in a reaction, then it is natural to conclude that any spontaneous reaction leads to an evolution of heat. In other words, any spontaneous reaction is supposed to be exothermic. However, we do know there are reactions that are endothermic. The reactions where heat is absorbed. The question is, but how does it happen? If the reaction is endothermic, that means by applying this logic, we must conclude the endothermic reaction is a transformation of more stable compounds to the more stable substances to less stable. But how? But that is kind of logically inconsistent, because how can the transformation from of more stable substances to less stable substances be spontaneous? Because we need to understand, we need to keep in mind that the term energy was specially designed, especially proposed to to describe spontaneous processes. So any spontaneous processes leads to a decrease of energy. The energy is decreases in any process which is spontaneous. If if extra energy is needed from the environment to start some process, that means this process is not spontaneous. So to understand the puzzle of endothermic reactions, we need to talk a little bit more about energy and the thermal effect of reactions. And to do that, we need to talk about such parameters as such quantities as enthalpy, which is denoted as delta H, free energy, delta G, and entropy, delta S. Does anybody know anything about that? Did anybody hear anything about these properties? Because usually in the chemical textbooks they introduce that, but the explanation is totally unsatisfactory. Let me try to explain that. First of all, the standard kind of apparatus which is used to explain majority of processes is processes which lead to heat transformation, thermal energy transformation, is the classical kind of the tool for thought experiments. With a cylinder, with a piston, and some material inside. Usually it is a gas composed of molecules, or so-called ideal gas. Ideal gas is a gas which is assumed to be, which is composed of molecules which are material points. They are very small and not interacting with each other. And all conclusions, and that's interesting, because all conclusions drawn from this model are equally applicable to chemical reactions, to many different processes. Because, for example, there is this strong connection between the gas pressure and the concentration of some reactant in a solution. Just try to think about that, but the linkage is quite direct and obvious. And that is why all conclusions drawn from this model can be finally applied to many chemical processes. And we can hit this, transfer some thermal energy to this system by applying some heat. And heat is the thermal energy transformed from one body to another. That is what we denote as Q. And now we have some, I don't know, now something happens here. Imagine something happens here. I don't know. For example, we burned we started some chemical reaction, the gas is burned, and some energy formed. How do we denote it? Usually, if nothing happens, if the piston cannot move, if the volume is constant, the change of energy is denoted as delta U. U is an internal energy, the energy of thermal motion of all atoms. So the sum of kinetic energy of all molecules. and potential if they can be deformed, but for ideal gas it doesn't work. However, if the piston can move, so if the delta U increases and the temperature increases, the pressure of gas goes up. The piston can move, and the gas expands. But what happens when the gas expands and the molecule hits the piston and bounces? As a result of this encounter, the piston moves slightly up. That means the initial velocity of molecule is greater than the final velocity. That means the molecule starts to move slower, and the internal energy decreases as a result of the gas expansion. Do you understand this? Does it make sense? Good. But when it is, so in other words, the molecules, by constantly hitting the piston, the molecules produce some pressure. And due to this pressure, the piston moves up, and now it is in this position. And that means the volume of the cylinder, of the gas, increases. That increases delta V, correct? But now, and during this process, some work was performed. And you know, we remember that work equals to force times distance, correct? But the distance is, okay. In our case, the distance is this. This is the distance. The force, so this is the distance. The force is the force equals to pressure times area, surface area, correct? And the volume is surface area of the cylinder times distance, correct? So this is a cylinder. The delta V is a cylinder with a height of delta D, and the base, this area is S. S times D. So that means we can replace force and distance with volume, with delta V, with change of the volume. So let's express force through pressure, Force, let's put this here. It will be P times S. Then let's calculate D. D equals to delta V divided by S, correct? Now we put this here. S and S cancel each other. So we get work equals to P delta V. So this is for solids, So if we are moving some solid body and we know the force and we can measure distance. This is for gases because there is no distances, right? For gas, we cannot speak about distance, but we can speak about volume. We can speak about volume change. And it's not easy to measure force, but easy to measure pressure. So this is the same as that. Understood? Do you have questions? Actually, that's a good time to ask questions because otherwise it will be just the online lecture, which you, because the most important opportunity here is to participate in a discussion. If something is not clear, just let me know. Okay, if that is clear, then answer the following question: is it possible that that we heat gas in the cylinder, but its temperature does not increase? We are heating the gas, but temperature does not change. Can it be possible? No idea. Okay. Let's.
Mark,
Yes.
by it doesn't heat up, do you mean it like completely doesn't heat up, or
Yeah, the
it
temperature
doesn't?
doesn't change at all. Can we imagine such an ideal process where temperature doesn't change at all?
You would have to change the pressure, I think, like the volume.
No, just imagine this. We are heating the gas from here, so the velocity of molecules increases. But when they hit the piston, they give all this excess of this velocity to the piston, and it moves up. So when the pressure stays the same, when the piston, which has no weight and no friction, can slide up, the expansion of gas during heat does not lead to any increase of internal energy, because all internal energy transformed to the piston, which becomes the external energy. So that means all the heat transforms to P delta V. So we maintain pressure at the same level, or we can artificially, I don't know, add a gauge here. And when we heat the gas and the temperature goes up, the pressure goes up. But when we pull the piston to maintain pressure at the same level, the temperature will stay the same. Does it make sense? Because the piston is moving, is sliding, and the molecules, okay, when we hit the cylinder from this side, the molecule accelerate due to encounter with the hot surface. But when we the molecules hit, accelerated molecules hit the piston here, they decelerate. So the piston, which is moving back, is actually acting as a cold surface. Because any molecule that hits it, it bounces with lower speed. So when we maintain pressure constant, heating does not lead to increase the temperature. All energy transforms to P delta V. In other words, to work. However, if we do not maintain pressure totally constant, it may the part of energy transfers to the internal energy. So, and this is called so that so this is a total energy that the system has. And why I am talking about all of that? I am talking about that because the typical experiment that we did here, like this. So we mixed two solutions. What is the common between all those experiments? All those experiments have one important common trait.
They all change color.
No, the mouth of the flask is open, but even if it's not open, the neck is not open, it's still connected to some device which maintains pressure, atmospheric pressure. The pressure is always constant. So overwhelming majority of chemical experiments are made at normal pressure, at constant pressure, which means if some heat evolves, forms in a reaction, it leads to increase of thermal energy, internal energy, and to expansion. But what is a piston in our case, in this case? Does it mean this device is different from that device? From that device? No, it doesn't, because there is still a piston here. We don't see it, but there is a piston. Because if some reaction leads to energy formation and thermal expansion, where the escaping gas comes to the atmosphere, to the Earth's atmosphere. That means if 1 liter of gas forms, that means our atmosphere, the Earth's atmosphere, becomes its volume increased by 1 liter. That means the diameter of the Earth slightly increased. That is tantamount to lifting the piston. And if we do the opposite process, the inverse process, if some gas is some gas is consumed in the reaction, the volume decreases, this energy is given back in the form of T delta V. So the volume slightly increases and kind of the imaginary piston has lifted. The work was done. The gas is consumed, the piston goes down. And that is why in chemical, when we measure a thermal effect, we always keep in mind the change of volume, because when the volume increases, the actual thermal effect will be lower than the thermal effect in the standard volume, in a fixed volume, and vice versa. And this quantity, which takes into account, this parameter which takes into account the volume change, the work done during the change of the volume, is called enthalpy, delta H. And that is why all textbooks do not, textbooks and handbooks, they do not provide figures of, when they provide figures of the heat effect of some reaction, they do not speak about delta U, the change of internal energy. They speak about delta H. And that is enthalpy. But now let's talk about more complicated subject. The second component. Actually, before we speak about, okay, let's speak about this. Imagine a more complicated experiment. We have a piston, a cylinder with a piston, and the gas inside, and the piece of ice here. And the temperature is 0 degrees. And we started to heat a system. We started to heat the system. We transform some thermal energy to this system, but the piston does not go up, so the volume does not change, and the temperature does not change. Instead, the ice starts to melt and nothing happens. We continue heating, but nothing happens until all the ice melts. Only after that, after all the ice becomes liquid, additional amount of heat leads to visible changes, which can manifest themselves either in the temperature. Okay, so this is a thermometer here. So we add the thermometer. So, and okay, the piston is sliding freely and weightless. That means if it does not move, that means the pressure does not change. Okay, so no change in temperature, no change in the pressure, and no change, which is visible as the no change in volume. And only after all the ice is molten, if the temperature starts to grow, or a piston goes up, or both. But what happens? Why does the energy, the heat transformed to this system doesn't change to any visible, doesn't lead to any visible changes until all the ice is molten? And where all this energy went? Does it mean all this energy was lost? All this energy that was spent for melting ice? What do you think? Is it lost? No. Why? How to demonstrate this energy was not lost?
I think isn't it? It's one of the laws of thermodynamics that energy can't be created or lost.
What?
Isn't it? I'm not any means a physics expert, but isn't one of the laws of thermodynamics that energy can't be like it can't be generated from absolutely nothing and can't just disappear?
Yes, but I mean, how to demonstrate the energy? Yeah, I understand what you mean, but how to demonstrate the energy was not lost? We can do a reverse process. If we start taking heat away from this system, what will happen? The ice, the water will start to freeze, and the same amount of heat will be recovered back. Or if we want the whole process, if you check the whole process, let's do it. The phase one, we transform some amount of heat to the system. Temperature does not change, no work is done, so delta U stays the same, but the ice melts. Step two, we continue heating. The ice has molten. We continue heating, and the piston moves, starts to move up. So now it is in this position. So we have the work equals to P delta V was done. And the temperature slightly went up, so some delta U. So now the energy is accumulated here as some delta U plus P delta V. But the part of energy is lost for melting ice. However, if we will reverse this process, if we will start in taking this heat away, so we attach it to the cooler, the heat will be transferred, will be started to transfer back. And the piston will start moving back, but if the piston moving here acts as a cold surface, the piston moving colder surface, moving back to here, it's acting as a hotter surface. So it will return, it will start to return the energy back. And but when we return to the initial state, the piston is returned to initial position, and we continue to take heat away, the water will start to freeze. But freezing water return the energy which was spent for thawing it. So finally, we get ice again. So now it's solid. We get the piston in the same position. We have the same temperature, and we recovered all the heat back. Does it make sense? Hello? We recovered, we took all this heat back. Do you understand it? Did you understand this point? Because I need you to understand it. Give me a reaction. But there is one difference. There is one difference here between the case where there is ice, there is ice, and there is no ice. If there is no ice and we do this process, the amount of work that we can obtain from this amount of heat is much greater than the amount of work that we obtain when the ice is added. So this ice takes some energy, the external energy, and stores it during melting, stores it in the form of a hidden energy. So this energy is still here. It can be recovered back, but it cannot be transformed to work. So the full energy and the hidden energy, the full energy is work plus thermal energy plus hidden energy. And hidden energy cannot be transformed to work to any visible changes. It leads to, it is spent to something that does not lead to any useful process. And if we subtract this hidden energy, we get a free energy. So total energy less hidden energy gives us the free energy. And this free energy is what is called delta G. After Gibbs, American physicist, who proposed it for the first time. And this free energy is a parameter whose change allows us to predict if some process is spontaneous or not. That is a very important concept. So I want you to ask me if something is not clear. I want you to ask me questions because it will be useful to you in future.
So if a reaction isn't spontaneous, would it go in the reverse or would it just not happen?
Reactions is spontaneous when the free energy goes down, when free energy decreases. But and that's just synonymous. Spontaneous reaction is a reaction where energy, more concretely, free energy, goes down. And now, if we understand that, and then the free energy we differ from total energy. From the total energy by some parameter, some amount, which is called the hidden energy. And now we need to know what the hidden energy is. We intuitively understand that because in our case, the hidden energy is energy which was needed to spend to melt ice. Ice melts and it leads to no useful changes. This process leads to no useful changes, but this energy can be recovered back when we come to the original state. So this energy does not disappear, but it is not useful. And to understand that, let's talk about temperature. What is the temperature? How do we measure the temperature? To measure temperature, we use a thermometer, right? That's some device. For this is the container with the gas. This is some device. What does it measure? How can we judge about temperature? It measures how frequently and how strongly the molecules hit its surface, right? Do you agree with this definition? Is it clear? Do you agree or you disagree? Great. But now answer me the following question. When the molecule hits the surface like this, is it the same as the molecule hits the surface like this? So its velocity is its speed is the same. The molecule A and the molecule B have the same velocity, but one of them hits the surface like this, another hits surface like this. Will the amount of energy transferred to thermometer be the same or different? If you think the same, say this. If not, say that. Hmm? Hello, guys.
I think it would be different because the angle at which it hits the surface.
Exactly. The faster you respond, the better the faster we move forward. So in reality, what we need to know, and this component of the speed, so this the tangential component of the speed is not important at all. So we need to know only this part, these components, right? So that means if the molecule move exactly parallel to surface, there is no heat exchange with the thermometer at all. So for our purpose, the molecule which moves like this has zero temperature. But fortunately for us, the molecules are moving randomly. and they move in all three directions with approximately the same proportion. So there are three components of velocity along the axis x, y, and z, and we can assume the molecule, each molecule has three different so-called freedom degrees of freedom. So it can move up, down, back, forward, and left, right, and all other movements can be kind of split, represented as a sum of these three different movements. And this is very important idea, the degree of freedom. You must understand it very well. Imagine the ant. Some imagine the ant living in on the kind of a rope, so it can move just in one direction. How many degrees of freedom does it have? One, two, or three?
I think one.
One. Okay, the same ant living on the surface. How many degrees of freedom does it have? Two.
Two.
Back, forward, right, left. Correct? Because if
Yes.
if it is moving, I don't know, to the northwest, that means it's a sum of motion to north and to the west, to the west. And after invention of flight, we have 3 degrees of freedom. Okay, after invention of multi-story buildings, we have three degrees of freedom, right? In contrast to ants, we can move back, forward, right, left, and up, down. And the same for molecules is the same. They have 3 degrees of freedom when it's ideal gas, when the molecule is just a ball. And approximately 1/3 of their internal energy, their energy of motion, is their internal energy of motion is shared evenly among all 3 degrees of freedom. 1/3 like this, 1/3 like this, and 1/3 like this. That doesn't mean they move only in those directions, but any motion, like if it's moving like this, it's a sum of that, and that, mixed in different proportions. I need you to firmly understand that, because that's a really important thing. So degrees of freedom does not mean they move only in those directions. Degrees of freedom means that all movement can be represented as the movement in this, and the sum of movements of these in these 4 directions. Similar how when we explain the directional map, move 10 steps on the west and 5 steps on the north. And this will be a correct description of my motion. I am moving northwest, but northwest, but my motion can be represented as the sum of these three motions. Okay, now imagine this thought experiment where there are many molecules here, many molecules here, and they are moving randomly. But we, I don't know, take a magic wand and told them and took away and prohibited them from moving in this direction. We took away this degree of freedom. So all molecules now are moving just in these 2 degrees. They have only just these 2 degrees of freedom. What happens to the temperature in that case? When the thermometer is here, the temperature immediately drops to absolute 0. But since molecules are still capable of moving and colliding with each other, their motion will be gradually restored. So the temperature was 0, but with time the temperature will go up, but it now will be just 2/3 of the original temperature, because 1/3 of energy is taken away. Now imagine a different, another situation. A molecule is not a ball. A molecule is a kind of a dumbbell. How many degrees of freedom this molecule has? Three.
Does it still have 3 because we're in a 3-dimensional universe, like according to us?
Yes, and one more, and one more. In total, 5. Does it make sense? I was asking myself, why the windows, which are insulating windows, good windows, which keep the temperature, keep heat very well, why the interface between two glasses is filled not by air, not with air, but with the xenon, the inert gas. And in my opinion, the reason is simple. The xenon is the gas, is a single atom gas. And it has just 3 degrees of freedom. Air is a diatomic gas. It has 5 degrees of freedom. Why it is important? Why it leads?
Because if there's the more degrees of freedom, the more energy it has. Like the more ways it can use its energy.
Actually, yes, but with one more detail. The rule according to which all the energy is evenly distributed among degrees of freedom, it relates not only to translation degrees, but back, forward, up, down, and so on, but to all degrees of freedom, including rotation. That means if imagine we have a gas which composed of ball-like molecules. They are round. They are just a single atom molecules. And we do, and then it has a temperature of, I don't know, 100 degrees. And now we, I don't know, do a magical trick. We transform this ball into a dumbbell of the same mass, of the same weight. And we change nothing. What happens to temperature? Will it change? Will it stay the same? Will it increase or will it decrease? What do you think? Okay. When the gas is just a gas molecule, is just a ball, it has 3 degrees of freedom, and only this degree of freedom transfer, or the energy accumulated in this degree of freedom is transferred to the thermometer and measured as a temperature, right? And the all kinetic energy is distributed evenly among 3 degrees of freedom. Now we transform the molecule from this to that. The mass is the same, the kinetic energy is the same, but now there are 5 degrees of freedom, but still this one is measurable as a temperature. What can you say about the temperature now?
Will the temperature decrease?
exactly by 1/5. Oh, okay. Now
Two
it was,
fifths.
yeah. It was 1/3. 1/3 of the total energy was measurable as a temperature. And now just 1/5. Yeah, it's easy to calculate how the temperature will decrease. But we did not add any energy. We did not take away any energy. We did not do anything with energy, right? We just transformed the shape of the molecule, just added 1 degree of freedom. Oh, 2 degrees of freedom. Understood? Now, let me. But there are even more complicated cases, right? The molecule can have much more degrees of freedom if it has a larger shape, or if a molecule transforms from solids to liquids, because in solid state, every atom stays in the crystal lattice and they move only like this, and they stay the same. Does not rotate, does not spin, does not move, just oscillate. It has exactly 3 degrees of freedom. When the material becomes liquid, molecules can move, molecule can slide, molecule can rotate. So the number of degrees of freedom increases dramatically. But only one of them is measurable as a temperature, is measurable as a heat. It can be transferred as a heat. So that means the increase of degrees of freedom, the number of degrees, the degrees of freedom are actually a storage of energy, which can be held by the body, by the physical body, but cannot be transformed into temperature and the work. Because remember, the work is something that is done when the object is pushing another object. So there is a strong connection between the work and the temperature. If only a small fraction of energy is measurable at the temperature, internal energy is measurable at the temperature, to the same extent it is applicable to work. Only small part of this energy, smaller part of this energy can be transformed into work. So, in other words, these degrees of freedom, extra degrees of freedom, which are keeping energy, internal energy, they are actually keeping a hidden energy. And how can we describe the amount of degrees of freedom? The more disordered the system, the degree of disorder is a measure of the numbers of degrees of freedom. And these degrees of disorder are called entropy. So these parameters, the third parameter, this one. But in addition to that, okay, let me do some demonstration. So this is the, I have a special program that may simulate the actual thermal motion. This is a water box with water, which can be simulated by calculating the real molecules in real situation, in near real conditions. So now I am showing you how molecules behave at this 100 degrees Celsius. Does everybody see it?
Yes. Also, I think it's actually Kelvin.
What?
I think it's Kelvin.
Yeah, Kelvin.
Oh, you said Celsius.
Oh, sorry. So this is a kind of like a Pac-Man in a Pac-Man game, so the periodic box when the molecule crosses the border of the box, it immediately appears here. So that's the model of the infinite water. But you see, they are fluctuating along some equilibrial position, and they are slightly bending and slightly rotating, right? So molecules have translational degrees of freedom, rotational degrees of freedom, 6, because they are angular, not linear, right? And they are kind of bending a little bit, so one more vibrational degree of freedom, right? So in total, they have 7 degrees of freedom. But now let's do the same calculations, but increase temperature, for example, 1000 degrees. Or even, let's do even higher. I don't know if it will work, but let's check. At 10,000 degrees Celsius or Kelvin, it doesn't matter in that case, right? You see, they, oh, that's too, okay, that's too high. It cannot work at this temperature. But you see, the motion is much more intense, and they, in addition to just bending, the bones start to stretch and they compress. So the additional degree of freedom is stretching of each bone. They move more intensely. The translational degrees of freedom takes more, accumulate more energy, and so on. That means at higher temperature, whereas there is a possibility to use all degrees of freedom to create a disorder, at lower temperature, only few of them are realized in reality. Whereas in higher temperature, much more degrees of freedom are kind of occupied. They are a real motion. That means not only the entropy itself, but a temperature is important in the process. So if we see that entropy, the number of degree of freedom increases, the actual hidden energy change depends on the temperature. At higher temperature, it is the hidden energy change is much stronger than at in lower temperature. So that means it, and the disorder effects are much more important at higher temperature than near the absolute zero. And in total, to summarize, delta G, the free energy that is measure of spontaneity of the reaction, is the sum of is the delta H, the enthalpy which you know, less T delta S, the hidden energy. And that is a measure of the parameter that this shows how spontaneous, if some reaction can be spontaneous. Now imagine the reaction leads to some thermal effect which is low, which is small, but it leads to a dramatic decrease of degrees of freedom. So this is big. So this is small or even negative, but this is big. What does it mean? That means delta G is still less than 0, because low thermal effect means high delta H, positive delta H. Normally delta H is negative. When heat evolves, we assume delta H is negative. When it is positive, so the heat is consumed, But this is very big. This is still less than 0. And the reaction is spontaneous. To summarize, if some reaction leads to dramatic decrease of the degree of disorder, dramatic decrease of entropy, even if its thermal effect is low or negative, it consumes heat. It still can be spontaneous. And that is why exothermic reactions are possible. So exothermic reactions are reactions where thermal energy is not formed, the amount of thermal energy is small, but due to dramatic increase of disorder, the delta G becomes negative and reaction is spontaneous. So that's a kind of a complicated concept, so I'm not sure I was able to explain everything, but if you want to ask questions, I will answer. No questions?
So a reaction that leads into the increase of degrees of freedom will be a spontaneous reaction?
No, not necessarily. Imagine if you if two atoms form a bond, and this bond is very strong, so low energy, they will interact, and the reaction is highly exothermic and spontaneous. But if imagine some transformation does not lead to decrease of energy, so more stable bonds break and less stable bonds form. But that leads to a dramatic increase of disorder. That's the increase of hidden energy. Oh, the decrease of hidden energy leads to a dramatic increase of disorder, and this reaction is still spontaneous. The simplest explanation is I don't know, the rope. When you take a rope, a straight rope, and put it, I don't know, put it into the bag and start to shake it, usually it becomes entangled. Very, very entangled. Although entangled and straight rope have the same energy. But this process, the process of entanglement, is more preferable because it leads to greater degree of increase of disorder. There's no energy involved. But since disorder is more preferable, the process will still grow. Again, that's not easy to understand, but if you need to try. Again, if you want, you may try to think about that and ask me later, because I'm available in by email or in Discord, or if you want, you may ask right now. Okay, so if no questions, if you believe I answered your questions, then good luck with the problem of the month. See you later. Bye.
Bye. Thank you.